Hello and welcome to The Daily Space. I am your host, Dr. Pamela Gay.
And I'm your host, Eric Mattis.
Most weekdays, the CosmoQuest team is here putting science in your brain. Today, however, is for Rocket Roundups. Before we get started, a quick programming note. We will have coverage of the launch of Soyuz MS-20 in the Daily Space episode tomorrow. Our team has a cutoff for stories and Rocket Roundups, so they don't scramble to put things together in the morning of the show. And that launch was after their cutoff. Let's get to everything else, shall we?
First up, on December 2nd at 2312 UTC, the Starlink 32 mission launched atop Falcon 9 booster 1060 from Space Launch Complex at Cape Canaveral Space Force Station in Florida. Let's watch the launch.
T-minus 5, 4, 3, 2, 1, 0, ignition, liftoff.
SpaceX's internal name for this mission was Starlink 4-3, despite this only being the second launch for this fourth shell. The rocket also carried 2 satellites for BlackSky Global's imaging constellation, resulting in only 48 Starlink satellites on board compared to the usual 53 for the current shell of the constellation. SpaceX keeps changing their naming scheme, so it's very hard to keep track at this point. This is the 9th flight for Booster 1060, which successfully landed on the drone ship A Shortfall of Gravitas. Both of the fairings were new and were fished from the water by SpaceX's multi-purpose support ship, Bob.
From one launch with many payloads to a Soyuz with only 2. On December 5th at 019 UTC, an Arianespace Soyuz 2.1B frigate launched 2 more satellites from Europe's Galileo navigation satellite from the Guiana Space Center in Kourou, French Guiana. Let's watch the launch. Galileo is the European Union's version of the US military's global positioning system, built to ensure Europe has a backup in case of problems with the US GPS. Galileo's signals are compatible with GPS, and many consumer or commercial devices can use signals from both GPS and Galileo, in addition to other global and regional sat-nav systems. These satellites, 27 and 28, are the first 2 Batch 3 satellites in the constellation. The final constellation will consist of 30 satellites, 24 active satellites, and 6 on-orbit spares. Spares are important because several clocks have failed on Galileo satellites. In 2017, a total of 9 rubidium and hydrogen clocks failed across the operational satellites, though no satellite lost more than 1 of each type. The same model of rubidium atomic clock was used on India's IRNSS-1A satellite. It lost all 3 of its clocks. The first test satellite for Galileo was GEOV-A, or Galileo In-Orbit Verification Element A. It was launched in late 2005 and only recently decommissioned in November 2021. It was a rush job to secure their frequency allocation on orbit before it expired in 2006. SpaceX's Tintin satellites served a similar purpose for the Starlink constellation. The operational satellites, like Galileo 27 and 28, contain the usual complement of 2 rubidium clocks and 2 hydrogen maser clocks, which are highly accurate frequency standards typical of a navigation satellite. A navigation satellite works by sending signals to receivers which contain the precise location of the satellite in orbit. It uses the same signal to tell the receivers the exact time it set the information, which it gets from those highly accurate clocks. The receiver then takes the signals from at least 3 satellites and does a bunch of math to determine the user's location. Relativity is required, folks. The more satellites the receiver can get signals from at one time, the more precisely the receiver's location can be determined. Just under 4 hours after launch, the 2 German-made satellites were separated from the frigate upper stage after 2 burns of that stage. The operational orbit for the Galileo satellites is just over 23,000 kilometers at an inclination of 57 degrees. Each satellite is taller than the average Christmas tree and weighs about 23 times as much, 732 kilograms.
Now we go to a rocket that weighs as much as the payload put into orbit by the previous one. On December 6th at 8:07 UTC, the German Aerospace Center, the DLR, launched an improved Malamute. Yes, you heard me right. Sounding rocket carrying the Matthias 10 mission from the European Space and Sounding Rocket Range, or S-Range, in northern Sweden. Both stages were identical improved Malamute motors stacked on top of each other. Total flight time was 15 minutes, and the rocket reached an altitude of 259 kilometers. The payload section landed under parachute and was recovered. Let's watch the launch. On board were 7 experiments ranging from materials research to radiation measurement. We don't have time to talk about all of them, so here are a few of my favorites. The first of these experiments is RTEC, which is short for Aerogel Technologies. It uses 5 furnaces to melt and then solidify different alloys in microgravity conditions. This avoids some problems which happen when casting metal in gravity and exposes problems which gravity compensates for, according to Dr. Sonja Steinbach at the DLR Institute for Material Physics in Space. In this way, we can develop more accurate models and better describe the relationships between process parameters, structure, and properties. RTEC previously flew on Matthias 8. MARS, or Metal-Based Additive Manufacturing for Space and Weightlessness Applications, manufactured a small piece of equipment using a metal 3D printer in flight. 3D printed metal structures have very high strength and corrosion resistance. Building structures in space has applications for making larger space stations in Earth orbit and bases on the surface of the Moon and Mars. The last experiment is the one that most interested me when I was putting together this episode. In it, researchers monitored how Trichoplax adhærens, often called plate animals for their flat appearance, reacted to the microgravity environment. This simple multicellular organism, which lacks both tissues and organs, has dedicated cells for sensing gravity. According to the researchers, the point of the experiment was to determine how this feature appeared in Trichoplax adhærens, and then developed in humans, as gravity has shaped the evolution of all life over billions of years on Earth. This experiment was filmed in flight, and it will be compared to the movements of ground-based control cells. Matthias 10 also carried 2 radiation detectors, which will be used on NASA's Artemis 1 mission to measure radiation on the way to the Moon. The output of both devices will be compared as part of qualifying them for the mission. After the break, China launches a small orbital rocket, and the largest Atlas V variant launches a satellite into high orbit.
On December 7th, at 0412 UTC, a Chinese Series 1 rocket launched 5 satellites into sun-synchronous orbit from the Qiashan Satellite Launch Center in China. Let's watch the launch. Series 1 is a 4-stage rocket with 3 solid stages and a liquid propellant 4th stage. On board were 5 satellites with missions ranging from different types of remote sensing to scientific research. This launch marked a milestone in Chinese commercial launches. This was the first time a Chinese company conducted a second successful orbital launch. The first Series 1 launch was over a year ago.
For our final launch of the week, a big rocket launched a satellite into a high-energy orbit. On December 7th at 10:19 BC, a United Launch Alliance Atlas V 551 launched from Space Launch Complex 41 at Cape Canaveral Space Force Station, carrying the Space Test Program 3 mission for the United States Space Force. Let's watch the launch.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And we have liftoff of the United Launch Alliance Atlas V rocket with the STP-3 mission for the United States Space Force.
Vehicle has cleared the tower and is beginning the pitch over program. And the RD-180 is throttling down slightly as expected. Engine response looks good. And passing 20 seconds into flight, the PU system has gone to closed loop control. SRB chamber pressures continue to look nominal. RD-180 pump speed and fuel injector pressures continue to look good. Mach 1, Atlas V is now supersonic.
Before we chat about the payloads, I'm going to nerd about the rocket for a second. It's pretty cool. You might be interested to learn that the Atlas V on this mission incorporated several improvements, mainly for ULA's future rocket, Vulcan Centaur. The most significant improvement was a new fairing fabrication technique called out-of-autoclave to make fairings faster and cheaper. As for the Centaur upper stage, it has 2 new systems, one which uses GPS to improve its already excellent orbital insertion accuracy, and another system to keep spacecraft batteries fully charged throughout the long mission. Now, on to the many payloads. STB-SAT-6 carries several experimental payloads for the Space Force, NASA, and the National Nuclear Security Administration. NASA's payload is the Laser Communication Relay Demonstration, which will test technologies for the next generation of data relay satellites. Laser communications have been tested in space for decades and have worked as far as 24 million miles from Earth on NASA's Messenger spacecraft. Compared to radio waves, laser communications have much higher bandwidth, often in the 1 billion bits or gigabit per second or higher range. LCRD is a relay only, meaning that it can't transmit data to other satellites. It can only transmit and receive data to ground stations. Currently, it will only be able to send data to 2 mountaintop ground stations, one on Haleakala in Hawaii and the other in California. Once a laser terminal is installed on the International Space Station, LCRD will be able to receive data from the ISS and retransmit that to the ground. The military payloads include one which will track nuclear detonations in space and in the atmosphere. Other payloads are for space weather. Still others are intended to assess the physical environment around the spacecraft, including how many objects might be nearby, what those objects are, how those objects may move, among other details. One of the payloads, the LDPE-1, which stands for Long Duration Propulsive Evolved Expendable Launch Vehicle Secondary Payload Adapter, carried other payloads. It's essentially a metal ring normally used to attach smaller satellites below a main satellite on the same rocket, turned into a satellite in its own right. None of those payloads were disclosed, though it was described as being capable of a 1 to 3 year mission, carrying experimental payloads for rapid risk reduction efforts to inform future programs. After the break, This Week in Rocket History features a suborbital flight of a monkey.
This week in rocket history, Little Joe 2. Before NASA launched their first human into space, they needed to prove that the Mercury capsule's launch escape system would function properly at different altitudes and speeds. They were in a rush, and NASA envisioned many tests, so whatever test vehicle that would be used needed to be cheap. This was accomplished by using as many existing components as possible. Engineers designed a booster called the Little Joe, using 4 existing solid rocket motors taken from a military missile, the MGM-29 Sergeant, and a new fuselage. The Little Joe was later scaled up into a Little Joe 2 for Apollo capsules. To keep costs low, it would not have an active guidance system. That meant that after the rocket ignited, there was no way to control it. The rocket was put on an angled launch rail and kept stable in flight by canted nozzles on the rockets and 4 large fins. The basic rocket could be augmented with 4 other boosters, and all 8 fired in different sequences for different amounts of thrust. By February 1959, the final design for the rocket was almost completed. Just 7 months later, in September, the first launch consisted of a booster, a mock-up capsule, and a live launch escape system. This first launch was not successful, but they proved the launch escape system worked. The launch escape tower fired 35 minutes before launch and carried the capsule away from both the pad and the booster. No one on the ground was injured. The error was traced back to poor wiring on the launch escape system. NASA realized that launching the booster with an active launch escape system on the first flight was too ambitious. So the second launch, Little Joe 6, carried only the booster with mock-up versions of both the capsule and launch escape system. That launch was successful. The next launch, Little Joe 2, had a bit more going on. The technical goals of Little Joe 2 were to escape the rocket at high Mach and measure the forces on the capsule, including pressure and heating from a space reentry. It would also carry all the biomedical experiments that doctors at the School of Aviation Medicine could think of to fly on a high-powered rocket. The main passenger was a live rhesus monkey named Sam, an acronym for the School of Aviation Medicine. Also on board were some barley seeds, cultures of the mold Neurospora crassa, rat nerve cells, and packets of insects. Little Joe 2 launched on December 4th, 1959 at noon local time. Booster burnout was at 30 kilometers, and momentum as well as firing of the escape tower carried the capsule to 85 kilometers. That altitude was only half of what was planned due to a windage error, or in other words, how wind affects the flight of a projectile. All test objectives were completed, but the overall result was disappointing. The engineers still did not get to test their launch escape system at maximum dynamic pressure. The biologists hardly learned anything new, though they did demonstrate the life support system in the capsule. Robert Galbraith, head of the Space Task Group at NASA, told the press of the relatively minor role of this particular task in the context of the Mercury program. After the break, we'll be back with our weekly statistics and random space fact. Stay tuned. To wrap things up, here's a running tally of a few spaceflight statistics for the current year. Toilets currently in space, 9. 4 installed on the International Space Station, 1 on the Crew Dragon, 2 on the Soyuzes, 1 on the Shenzhou, and 1 on the Tianhe. Total 2021 orbital launch attempts, 126, including 9 failures. Total satellites from launches, 1,653. We keep track of orbital launches by where they launched from, also known as spaceport. Here's the breakdown. China 48, USA 41, Kazakhstan 11, Russia 9, French Guiana 6, New Zealand 5, Japan 2, India 2, Iran 1, South Korea 1. Your random space fact is that the large asteroids Ceres and Pallas have a near 1-to-1 orbital resonance. This means they both complete an orbit in the same amount of time, though Pallas's orbit is much more inclined, 34.6 degrees, and eccentric than Ceres. This has been the Daily Space.
You can find more information on all of our stories, including images, at dailyspace.org. As always, we are here thanks to the donations of people like you. If you like our content, please consider joining our Patreon at patreon.com/CosmoQuestX.